today's topic is strength. So, in engineering design, the thing we are really interested in is the strength, right? So, we should design the safer structure, right? It means strength should not fail within some loading condition, external load. So then we need to know when structure fail or when material fail. So strength is so let me give you a definition of strength. The strength of a material So the strength of a material is its own ability. It means strength is a property of a material. It depends on the material, right? Strength of a rubber, strength of a steel, strength of aluminum are all the different. So, and to withstand the applied stress without failure. Okay? So, here the strengths here the failure mean the material failure, right? So there are many scale of failure. So material failure mean the very local level failure. So there are also structural level failure. It's a very large scale failure. So now we are talking about local failure. Okay, we are saying it's a material failure. So material failure really depends on strength. And again, strength is a property of some material, right? You know that, right? When we give the external force, some material fail, some material doesn't fail, right? So it's a property of a material. Okay, so long times ago, and people try to define the strain. So people wanted to know how material fail, right? So they made a lot of different strength criteria. Okay. So strength criteria. So today's topic is I'm gonna write down again. So people define some function f. This function f is a function of stress, right? So function of component of stress tensor. And this some function of stress tensor should be smaller than 0 for all the possible stress. This means all, right? We are saying this is a material strength domain. And material stress domain defining admissible stress state. So this means all stress state must be within the strength domain of the material. So now this is looks conceptual. So stress field, stress tensor, stress field should satisfy this condition. And material where when f that function is 0. So usually we define the strength with the function f. So the other name of function f is a load function or loading function. So this function should be always smaller than 0 or equal to 0. And when this function becomes 0, it means material fail. Okay? So now it's very hard to understand for you, but if I give you example, you can very easily understand. So strength criterion has in the form of this setting, and let me think about the first and easiest strength criterion, tension cutoff. Cutoff criterion. So tension cutoff strength criterion define the function f, okay, equal. So I like define this. Principal stress, the biggest principal stress is principal stress sigma 1 minus f t is smaller than 0. This is a function. So biggest principal stress minus this is some strength parameter. This is given from the material test. Should be smaller than 0. And failure happen when stress, the principal stress 1 is the same to Ft. Okay? So this is a maximum principal stress. And we are saying Ft is a tensile strength. This strength is depends on the material. So we need to do some experiment. Okay? So admissible stress means the maximum principal stress cannot be bigger than tensile strength, right? If the material follow the tension cutoff criteria. So, for example, let me consider we have some material, and I'm going to give some tension. Okay, sigma. That's the direct tension test. For that test, we have a stress tensor 0, 0, 0, 0, 0. Right? Right? And 1 equal, let's say, this is okay. And sigma 2 and sigma 3, principal stress 2, 3, 0. And we can draw that in Mohr circle, tau, sigma, right? This is sigma 1. So I'm going to increase this sigma 1. So if I change here this sigma, the circle will change, right? Something like this, and it can be bigger. In direct tension test, all the stress state is under this circle, right? Circle size bigger and become bigger and smaller, depending on the applied tension, right? And so let's think like this. So I'm going to increase that stress. Then this circle become bigger and bigger, right? And then this stress meet some criteria here. This means the function 1 equal ft. Then material pair. So this is the condition. F sigma equal 0. So if there is some material, okay, which follow the rule tension cutoff criteria, okay, stress state, the old circle, okay, should be this range. So this circle cannot be bigger than cannot be bigger than this line, ft. If it's bigger, that's not admissible. That's not possible stress state. And maximum is this circle, right? So when this circle reaches to the maximum, we define the material failure, right? So that's the tension cutoff. Very simple. So actually, if we do some experiment, we can draw stress-strain curve, strain and stress. So, and there are going to be some linear range and fail. So we are saying this is a FT. fail mean when we there is no stress increase. So I increase stress, but at this point, even I didn't increase stress, strain happened. So material, so displacement material increase very rapidly without additional stress increment, right? This means fail. Okay? So tension cutoff criteria is just one of criteria. There are a lot of possible criteria, and that's the simplest strength criteria. Let me consider a little bit complicated one. More than that, Tresca. Second Tresca. Criteria. So the other name is that maximum shear stress criteria. So tension cutoff criteria, important stress is a principal stress. This is normal stress, right? And Tresca criteria, failure is governed by shear stress. In tension cutoff, failure is governed by normal stress, right? But tension cutoff Tresca criteria, failure is governed by shear stress. So its definition is that F can be defined by F stress equal 1 minus 3 minus sigma 0, just smaller than 0. Stress, principal stress 1 minus 3 mean the diameter of a Mohr circle, right? And half of diameter of Mohr circle is a maximum shear, right? And or equal tau minus 0 over 2. Actually, this tau is same to the 2, right? So Tresca criterion is governed by here shear stress maximum. When the maximum shear stress is same to the some material parameter, we can think material failure. So in tension cutoff criteria, Ft was a material parameter to define the strength, and Tresca sigma 0 over 2 is a material parameter to define the strength, right? So for both material strength criteria, we have only one material parameter, right? So we need only one material test, right? You know some material test machine, okay? Direct tension test. Okay, so one equal T square minus sigma square, right? This gives all the shear. So let's consider that direct tension test. So this means, that graph means tau, here tau, okay, sigma. This tau should be within plus minus sigma 0 over 2. So here tau equal sigma 0 over 2. Here tau equal minus 2 over sigma 0. So Mohr circle should exist in this range, right? So for direct tension test, okay? So when the stress is small, this circle, and stress become bigger, right? And this is a maximum size of Mohr circle, which is possible. And in direct tension test, if the Mohr circle meet this line or this line, material fail, right? We define material fail. And how about the simple shear case? Simple shear case means we have a transpose shear tau and tau, right? In this case, here sigma tau. The biggest Mohr circle looks like this, right? And here we have a small Mohr circle inside. If we increase the shear, this circle increases. So this is when this circle, the biggest Mohr circle, meet this upper line and lower line, material fail. This is a Tresca criteria. So let's consider this case, the direct tension test case. So we are tensioning the material like this, right? And material fail at this point, right? This is a 90 degree. This direction is a principal stress direction. So principal stress direction is this. And this is failure happen to the surface. So surface, this is surface corresponding to the principal stress direction, right? This line and this line is corresponding to each other. And at the 90 degree, material fail mean here 45 degree material. The failure line is 45 degree. Material fail on some surface. So material can fail here or here. So it means material fail through this line 45 degree or minus 45 degree. So material fail like this. This is failure line, failure surface. So if you understand the Mohr circle and stress criterion, you can find the failure surface too, right? We can find for when material fail, okay? Where material fail. Also, the direction of the failure. So failure surface give us a direction of failure. Okay? A little complicated. So I introduced two material criteria, and I like to talk about two more today. Third one. Coulomb. Criterion. Coulomb criterion is very widely used. And definition of a function f equal tau. This is shear stress plus normal stress and tangent some angle minus c is smaller than 0. Here tau equal t square minus. So tau comes from the Trias criteria, right? And the normal stress comes from the tension cutoff criteria. And we have two material parameters. So how many material tests should we do? 2 times. So we have two material parameters, C, its name is cohesion, and this is friction angle. So we have two material parameters. You can find that material parameter by performing two independent material tests, right? And very important thing that if that friction angle is 0 and C equal 2, then what happens? This Coulomb material criteria become Tresca, right? It means the Coulomb criteria is a general version of Tresca. Or if the angle go to pi over 2 and C tangent equal Ft, and criteria become tension cutoff. So this Coulomb criteria include the Tresca and tension cutoff. And so, in other words, Tresca and tension cutoff is a special case of Coulomb. So you understand the first, right? You understand the second one? So to drive the second one, in this equation, you can divide by the all three terms with a tangent. So tangent over tau plus sigma minus C, right? Here, when the friction angle go to 90 degree. This go to infinity, right? So this become 0, right? So we have only sigma here. If we define this term, Ft, strength criteria become tension cutoff, right? So in Mosuku, we can draw this criteria too. So more plane, tau, sigma. This is a criteria. So more circle should exist within this area here. It cannot. Okay. So this criteria defined by two lines, this line and this line, right? So if this angle becomes 0, okay, this line become parallel. Row line become parallel. So it becomes Tresca. Okay? If this line, this angle go to 90 degree, this line become vertical, this line vertical. Right? So this criterion become tension cutoff. So Mo Coulomb is a general version of previous two strength criteria. And circle. So for example, direct tension test. So this is a more circle for direct tension test. And if the stress increase, circle increase, then this is the maximum circle we can have, right? And material failure surface can be defined by this angle, because material fail here and here. We can find, okay, geometrically. This is direct tension. So we are pulling the material. How about direct compression? What happens if we compressed both? Now what happens? Same circle, but that circle we have in this side, right? So in compression test, the circle become much bigger, right? So both are actually same test, but strength depends on normal stress, magnitude of normal stress. So in compression case, material strength, so we have a different Mohr circle, size of Mohr circle. So we are saying this is a pressure dependent strength criteria. Direct tension test case, right? Tresca case, tension, compression, same size, right? And tension cut-off case, material only fail in tension, doesn't fail in compression, right? So this is okay, pressure sensitive strength criteria. Pressure. In general, material easily fail for tension rather than compression. In general, actually it depends on the material type, but in general, many material more easily fail in tension case. So this Mohr-Coulomb criteria and tension cut-off criteria makes sense. And this criteria is derived from the lot of material tests, right? So Mohr and Coulomb and Tresca did a lot of material tests, right? Again and again, and finally they find this kind of material criteria. After, for example, so Mohr did a lot of direct tension tests, and then he calculated the principal stress and then put here he put some data on Mohr plane, and then he finally find material fail like this. Okay. Okay, so Mohr-Coulomb material. So maybe now I like to talk about the most important failure criteria, which is used for steel structure. So you design pressure tank, right? So how did you find whether material fail or not? Huh? How did you determine? Huh? Effective stress? Maybe. I'm really sure you use some material criteria. You remember? So if you do some finite element analysis, you will have a stress. So 6 stress, right? And then if you get the stress, how can you find? How can you know this material fail or not? Huh? You did for your master thesis, right? No? No? Okay. So the following material criteria, strength criteria, is very important for steel structure. Bone mices. Bone mices. So equation is like that. So F equal J2 minus K smaller than 0. So now we are using J2. What's J2? Second, deviate stress invariant, right? So when square root J2 it becomes some material parameter K, material fail, right? We can define like that. So to determine whether the material fail or not, we should calculate J2. J2 is the second invariant, or deviate stress. What's the deviate stress? Okay? What's the deviate stress? How we calculate? We calculate deviate stress by subtracting hydrostatic part from the stress tensor, right? So also that maybe that's the name of a person. Von Mises did a lot of tests, okay? And then he finds this strength criteria, von Mises. And we need to understand the meaning of that strength criteria here. Let's draw principal stress space. This is a principal stress space defined by principal stress direction N1, N2, N3. Right? So in principal stress states, all the stress tensor become just can be represented by three value. Normal, three the principal stress. And for hydrostatic state, three principal stress is the same. So that should be on this line. This is a hydrostatic axis. 1, root 3, 1, 1, 1. Hydrostatic axis. So if some stress state is on this line, this is a hydrostatic state, right? Okay, then let's say some arbitrary stress state by point P. Here, stress 1, 2, 3. Then this is vector which represent the stress state, and this vector can be divided by two parts. One is some vector on the hydrostatic axis, and this is distance, and the other thing is this pattern. So here, something like that. So let's say here O, and this point is N, this is P. Okay, maybe I need to do this job in the next class.